Just like a playground has rules, the universe follows the laws of physics. Humans are innately curious, and we often get bored with the familiar games. But to be able to discover new horizons, we must understand the very fabric of existence, space-time, and the laws that define how everything in this mysterious universe behaves. We know objects can move through space, but as they do, they also journey through the ever-present dimension of time. Everything works quite intuitively when things travel slowly. It's only when an object approaches the speed of light that strange phenomena starts to happen. Would you be able to see your reflection in a mirror while traveling at the speed of light? How could the universe rewrite events if you were to go back in time and try changing them? And what's the solution to the grandfather paradox? In our vast universe, the speed of light serves as a fundamental limit for how quickly anything can move or any process can occur. Even on a tiny molecular level, information is transmitted at the speed of light. But we still haven't measured it. We only have data on the two-way trip, which involves bouncing light off a mirror to calculate its round trip time. So it's just an assumption that the speed of light is constant in both directions. But what if it's not? One day, an important message is sent from Earth to the first Mars settlers. The message reads, "This signal was sent at midnight. Adjust your clocks accordingly." We know the speed of light takes 24 minutes to reach Mars and return to Earth. The Mars settlers assume that the one-way speed of light is exactly half the round-trip speed and adjust their clocks to 12 minutes past midnight upon receiving the message. But in this scenario, light traveled at only 50% of its usual velocity to Mars, so it took 24 minutes to reach the red planet. Unaware of the discrepancy, the Mars settlers respond, "Clock adjusted, message sent at 12 minutes past midnight." Meanwhile, the signal on its way back to Earth travels instantaneously. Earth's clock now shows 24 minutes past 12 when scientists receive the message. They assume it took 12 minutes for the Martian signal to arrive, so they think everything went well, even though there's a 12-minute time difference. So you can see by this example that understanding the speed of light is crucial to unlocking the enigmatic nature of time. But what exactly is time, and how do we define it? When we think of time, we imagine the changing of the seasons or see it as a handy tool that helps us agree on when and where we're going to meet someone. Although that ticking clock is just another representation of movement, the movement of our planet around the sun, to be precise. The problem is, moving through space and time doesn't seem to be governed by the same rules. There's a limit on how fast you can go in 3 dimensions of space, and that's 186,282 miles per second. But is there such a boundary for how fast or slow time can progress? The Earth orbits the Sun relatively slowly, yet even here on our planet, there's no universal clock we can all use as a common reference. Time seems to flow differently for all of us, something Einstein's theory of general relativity predicted. To notice just how weird this connection between speed and time is, you need to watch things that move extremely fast. It's only then that remarkable paradoxes start to reveal themselves. The faster an object ventures through space, the more it slows its progression through the fabric of time, a phenomenon known as relativistic time dilation. So what happens if you travel at the maximum speed? Photons don't have any mass, so they always move at exactly the speed of light, not slower, not faster, and so time doesn't exist for them. Their journey is instantaneous, even though from our perspective, we notice how time goes by as they traverse space. How does this work? Consider a hypothetical scenario where a rocket travels at 99.99% the speed of light. A passenger on board that rocket throws a ball in the direction of the rocket's movement. The velocities of the rocket and the ball add up, something we would expect from classical Newtonian physics. But if the passenger switched on a flashlight instead, the speed of light wouldn't gain any boost. Both the rocket crew and an observer standing on Earth would record the same speed for the flashlight's beam, since this speed is constant and independent of the velocity of its source. But there's a problem. If the speed of light isn't changing, something else should. Time. Now picture this. You're riding a futuristic motorcycle down an incredibly long, incredibly empty road at the speed of light. You decide to look at your reflection in a side mirror, but there's a catch. The mirror is also moving at the speed of light. So how would the light reflecting off your face even catch up? If you can see your reflection, it would appear to someone watching you that the light bouncing off your face is moving faster than the speed of light, which contradicts the laws of physics. However, no reflection would suggest that the speed of light is not constant. In this case, someone standing beside the road would observe the light moving slower than you do, unable to reach the mirror. To avoid these glitches in the matrix and ensure a consistent measurement of the speed of light for all observers, the universe has come up with a few tricks. When an object approaches the speed of light, not only does its time seem to slow down for us, but we also witness the object shrinking in length. Another visual distortion is when a moving object rotates itself, something called the Terrell-Penrose effect. Although, despite the common misconception, it won't gain any additional mass, rather, it will gain kinetic energy. Yet, the weirdest thing of all is that these changes would only be real to us. For a person traveling at a speed close to c, everything would stay the same. They would feel motionless, time would flow normally, and their body would preserve its usual length. To the rocket's passenger, what's outside the cabin window would seem to act weird and transform or distort. There's no definitive way to tell who's experiencing these strange, almost mystical distortions. The absence of a shared objective frame of reference leaves us in a puzzling situation. Since motion is relative, the distinction between who moves and who remains stationary becomes elusive. It's as if each of us wears a unique set of goggles, offering a slightly different version of reality. Unlike optical illusions, time dilation is a real and irreversible phenomenon. As the rocket slows down and comes to a halt, the crew and an observer on Earth can finally compare their clocks and notice the difference. Time is an unidirectional flow pushing us forward. We've already discovered how to manipulate it to progress faster through time. But what about going against its natural course, into the past? If time passes by at its full rate when we're still, and stops at exactly the speed of light, it's only logical to assume that backwards time travel would require reaching superluminal speeds. For all we know, the speed of light is a unified speed limit, both for moving through time and space. The only decision you have is how you distribute that amount of speed between these dimensions. Even today, we can already look back in time. The light takes approximately 1.3 seconds to travel from the moon to our planet. So every time we look at our satellite, we see the way it was a little over a second ago. And if the distance is much greater than that, we can observe a more distant past. So let's imagine that one day we could not only look back in time, but travel there without breaking the cosmic velocity boundary. Scientists have already suggested several hypotheses on how this can be done. One of these ideas is a megastructure called the Tipler cylinder. An infinitely long tube with around 10 or more solar masses squeezed together and spinning several billion times per minute would be able to warp time around it. If in a very distant future we managed to build such a megastructure and flew around the cylinder in a strict spiral course along the direction of its rotation, we'd essentially travel back in time. The closer our ship would get to the cylinder with a density that of a black hole, the faster into the past we'd be able to move. And once we've calculated the time required to spend in this circular movement, we'd simply have to shift the spacecraft away from the Tipler time machine. There's a possibility that, contrary to our understanding, time doesn't have a linear direction. If space and time is one, there may be no difference between then and there, or now and here. According to an idea known as the block universe theory or eternalism, time is akin to a block, and every moment, past, present, and future, exists on equal footing, just like there is space outside of the visible universe, even though we cannot reach it. If true, the laws of physics in such a universe would allow for traveling into the past. although we wouldn't be able to affect the chain of events as much as we'd like. If the future already exists, then all events are predetermined and inevitable, and people who live in this universe have no free will. Such a world would be full of casualty loops. The casualty loop creates a self-perpetuating closed cycle where events in the future influence events in the past and vice versa. One day, while visiting an old bookstore, you discover a captivating notepad hidden amongst the shelves. It sparks your inspiration, leading you to start writing. With time, you become a renowned author and you decide to create a book. As you walk home on the same day you finish writing it, you pass by an old bookstore and the draft slips from your messenger bag unnoticed. The store's owner finds it and decides to put it on the shelves. This is the same notepad you stumbled upon all those years ago. In this scenario, the loop itself dictates the sequence of events, leaving no room for alternative choices or deviations from the course of events. Some paradoxes in self-contained time loops are even wider. Picture this. One day you receive an enigmatic letter at your doorstep, containing detailed instructions on how to build a time machine. The letter lacks any sender information, leaving you puzzled about its origin. Years pass and you finally construct a fully functional time machine. As you stand before the creation of a technological miracle, you think of the letter's mysterious arrival. Fueled by curiosity and the desire to solve the enigma, you embark on a journey back in time. Upon reaching the past, you seek out your younger self and deliver the very letter you had once received. As you do so, you discover that you yourself was the sender. But the letter's origin remains unclear. It's forever trapped in a loop of self-reference with no clear beginning or ending. It's only through the discovery of the letter that the time machine can be built, and yet it is the existence of the time machine that leads to the revelation of the letter. Naturally, an object without a creator in the bootstrap paradox leads to another problem, the restoration paradox. An object trapped in the perpetual cycle of time loop will inevitably age and deteriorate, reaching a state where it can no longer be used to sustain the existence of the loop. Time travel might seem to offer a way to restore it, but without knowing its creator or when it was created, we don't know its initial state either. Even if you were fully conscious of your journey into the past and had a clear plan of actions, there would still be many paradoxes. In the famous grandfather paradox, you wouldn't be able to travel into the past and keep your grandparents from meeting, as this would contradict your very existence, and so the ability to use a time machine. So, isn't it possible for a hypothetical time traveler to change at least something in the past? Recent research suggests that a paradox-free time travel is hypothetically possible. You'd still be able to travel back in time and do basically anything. The trick is that the timeline would self-correct in a way that the result will always stay the same. Such a universe would not allow for paradoxes of any nature to exist in the first place, essentially rewriting past and thus future events. With the grandfather paradox, something truly bizarre would happen. You might still be able to do whatever it is you planned, but once you return to your present time, you would find out that the man you terminated wasn't actually your grandfather. Or you might discover he's still alive, but he's changed and has scars from your termination attempt. Regardless of what you attempt to change, you could only alter how something happens, but never the result of this event. Although recently scientists have put forward a solution to the grandfather paradox, in the world of quantum mechanics, there's a puzzling phenomenon known as quantum superposition. At the subatomic level, particles can exist in multiple states simultaneously, like being in two places at once or having two different properties at the same time. Researchers applied this concept to the grandfather paradox and discovered something interesting. A time traveler who embarks on a mission to alter the past would appear in an extraordinary state, existing in multiple versions of the same past simultaneously. In one of these versions, they failed to arrange events that would lead to their grandfather's demise, so history proceeds along its natural course. In another version of the past, a time traveler succeeds on his mission. The two states of the past are equally real, but the final outcome remains undetermined until somebody measures or observes it. Both possibilities persist simultaneously, like parallel threads in the fabric of time. The resolution occurs the moment this loop is observed. When this happens, the universe decides on one of the two outcomes. And this concept is not something new for scientists, nor is it purely theoretical. This is exactly what happens with the famous double-slit experiment. Right at this moment, quantum superposition takes place in the sun's core. It's possible that the universe always exists in a superposition of two states, or maybe there are more than just two. Perhaps the reason why we cannot explain the order of events in these paradoxes is because time isn't linear. But there is one idea that can resolve the paradoxical nature of backwards time travel, while also providing a solution to the free will problem. It's known as the many worlds interpretation. The many worlds interpretation provides an intriguing perspective on the bootstrap paradox, where the origin of an object becomes clear. Imagine a series of universes unveiling each time you travel into the past. You write a letter with time machine instructions in the universe 1. As you travel to the past, a new universe 2 branches off from the original one. Upon arriving in the past of universe 2, you encounter one of the infinite versions of your past self and hand over the letter. The you from this universe grows up into becoming a physicist, builds a time machine, and creates a universe 3, where yet another version of you will get the same letter. That's when you launch the cycle which perpetuates endlessly, forming an intricate web of universes, each featuring its own version of events. What if even right now, with every event in the universe that allows for multiple outcomes, a separate parallel universe emerges for each of these potential results? In mathematics, there's a thought experiment on probability. It's known as the infinite monkey theorem, and it suggests that given a monkey has an infinite number of attempts and enough time, it would eventually type out a precise copy of William Shakespeare's works, or just any other piece of literature. If something as highly improbable as this ever happened in our universe, it would be a direct proof of the many worlds theory. Next time you encounter an extraordinarily unlikely event, consider this. What are the chances that the universe flipped a coin and it defied all odds by landing neither on heads nor tails, but perfectly balanced on its side? Do you think we'll ever be able to make time flow backwards? Or is time just an illusion that helps us navigate this confusing world? Sound off in the comments and stay tuned here for more content like this. Thanks for watching.